This is part two of our review for the final exam, and we're discussing in this part the concept of free fall, which has to do with objects that are in the air exclusively under the influence of gravity. In other words, there's nothing pushing or shoving or trying to stop the ball other than gravity, and perhaps maybe a little air resistance, but in these cases what we're talking about is something that doesn't have much air resistance. It's just gravity what's going on here as far as what's influencing the object. So let's consider a ball that is rising up in the air and coming back down. So we have a ball that's rising and falling. So along this path, one of the things we have to first note is if you throw a ball up in the air, it's going to go up. It's immediately going to start to slow down. And why do you think that is? Well, it's going to slow down. As soon as you throw it up in the air, it's going to slow down because the velocity, let's look at it here, the velocity here is in the positive direction, but we know that there's something called the acceleration due to gravity that happens to always be pointed down, and this is the acceleration due to gravity, and remember it's negative 9.8 meters per second squared. So it's directed downward and its magnitude is 9.8. So remember what we said before in the last review, that if you have an acceleration that's the opposite direction to the velocity, the object's going to slow down. So when you start to throw a ball up in the air, immediately it's going to start to slow up because the acceleration, which is due to gravity, is in the direction opposite to the velocity. So we got this slowing effect until it reaches the very, very peak of its flight. At the very top, the velocity is going to be 0. But let me ask you this question. Is the acceleration at this very top 0? And you might think so because it's stopped and you say, well, it's not moving, so it must not be accelerating anymore. But the truth of the matter is that we've discussed this with free-falling objects and says because gravity is always present and always operating on things, that even when it's at its top point and the velocity is 0, there is still this acceleration due to gravity of 9.8 pointing straight down. So no matter where you are in the flight, whether the ball is rising or falling or right at the tippy top, the acceleration is always going to be 9.8 meters per second squared downward. So what we have to come away with this is that we have a constant acceleration, and that is 9.8 meters per second squared downward. No matter where you are, whether you're at the launch, at the very top where the velocity might temporarily be 0, or on its way down, the acceleration in each point is always 9.8. And I remember telling you, no matter where you are, we're going to say this thing has acceleration, even if it's at the top and its velocity is 0. So we know that, and we know the number for our acceleration due to gravity is this 9.8 number. What happens if we're in a vacuum? Let's say we've got a tube and we take out all the air. So we're in a vacuum, and vacuum simply means you suck out all the air. Like a vacuum cleaner, it sucks out all the air. So there's no air. So there's no air. That's what vacuum means. And we have a stone, and maybe we have a feather. And I'm going to drop them from the same height of this tube, height h. So the question is, which is going to hit the bottom of the tube first? It turns out that if there's no air, then there's no air resistance, and gravity has the same acceleration for both the rock and the feather. So both of them are going to fall at the very same rate. They are going to both fall the exact same distance at the exact same time, and they will hit exactly together at the same time. So the rock isn't going to hit the ground first or the bottom of the tube. They will both hit the tube's bottom at the same time if there's no air. Now, of course, if you put air in there, you're going to have air resistance. The rock's going to hit first. But in a vacuum, both are going to hit the bottom at the same time. And this is because everything accelerates with the same acceleration due to gravity, which is that negative 9.8 meters per second squared. That means we'll have equal displacements in equal time intervals. Okay? Equal displacements in equal time intervals. That means they're going to fall exactly the same delta y's at the same time and hit together. So then we talked about, next thing we talked about was the difference between vector and scalar quantities. So a vector is something that has both magnitude and direction. And a scalar simply has magnitude. Sorry, I'm writing really bad today. But scalar has magnitude only. The vector has both direction and magnitude. And we show a vector with an arrow, where the length of the vector is the magnitude, and the direction, of course, is just the direction that the arrow is pointing. So some examples of a vector would be velocity, acceleration, force. These types of things have both magnitude and direction. Scalars only have magnitude. Magnitude is just the amount. So the number of leaves on a tree, temperature, things like mass. These were all scalar quantities. Work is also a scalar quantity because it's a matter of energy, and so forth. So these are all scalar quantities. Now the last thing that I want to put on this videotape, if I can get it in here somewhere, let's see if I can fit it in, is this concept of projectile motion. So maybe we'll just do this. Maybe let's say, how do we do it? Image clear, do that, and back. Okay, good. Projectile motion in 2D, 2 dimensions. So let's say we have a height and a length. So here's our x and here's our y, and we have some object traveling like that. We talked about cannons being fired and baseballs being thrown through the air, and let's say you got a ball that's going through the air, it's going up and then it's going back down. So this is projectile motion. When we have a change in motion in 2 dimensions and we are strictly under the influence of gravity. That means there's nothing else moving the ball. There's no engine thrusts here, no forces other than gravity once it's in the air. So it's flying through the air here, and gravity is the only force on the object. That's projectile motion, strictly under the influence of gravity in 2 dimensions. And when a ball, let's say this is our ball here. What color can I use here? This is getting, okay, here. So our ball is here. It has 2 components to its velocity, doesn't it? It has an x component, velocity in the x direction, and it has a component in the y direction. On its way up, the y component is directed upward. It's positive. When the ball is on its way down, the y component is negative, but our x component does not change. So remember projectile motion when we talked about it, and we says the one thing about projectile motion is that the x component always stays the same for the whole trip. The y component can change. At what point along this path would the y component of the velocity be 0? Well, if you said at the very top of its flight path, it's going up like this, right at the top, the y component is 0. Immediately after, when it starts to move on its way down, then the y component is negative. Immediately before, it's still on its way up, so the y component to the velocity is positive, but right at the very top, that's when the y component to the velocity is 0. So next video, we're going to continue with the concepts of force, because that's where we moved next during our year's study of mechanics, the study of objects in motion.